When dealing with a 480 delta to 240 delta dry type transformer, especially one equipped with a 5% neutral, understanding the correct grounding procedure is critical for safety and proper operation. It's essential to recognize that even though one of the secondary phase conductors must be grounded to establish a ground reference for short circuit and overcurrent protection, the presence of a 5% neutral introduces specific considerations. Firstly, the 5% neutral is intentionally designed with a reduced current carrying capacity compared to the phase conductors. This design limitation is a deliberate engineering choice reflecting the expected role of the neutral in the system. Secondly, the primary purpose of a neutral conductor, in general, is to carry the unbalanced currents that arise from unequal loading across the phases in a three-phase system. However, in this specific configuration with a 5% neutral, its capability to handle significant fault currents is substantially limited. Now, concerning grounding practices, it is imperative to refrain from bonding the secondary to the 5% neutral. The reduced size of this neutral conductor means it is not adequately sized to safely carry the high fault currents that can occur during a short circuit or ground fault condition. Attempting to use the 5% neutral as the ground reference could lead to overheating, conductor damage, and potentially create a severe safety hazard. Instead of using the 5% neutral for grounding, the recommended and safe practice is to bond one of the secondary phase conductors to establish the ground reference. This approach ensures a robust and reliable ground path for fault current. By bonding a phase conductor, you are creating a direct, low impedance path for fault current to flow back to the source, which in this case is the transformer. This low impedance path is critical for the rapid operation of overcurrent protection devices, such as circuit breakers or fuses. When a fault occurs, the high fault current will quickly trip the overcurrent device, isolating the faulted circuit and minimizing damage to equipment and preventing electrical shock hazards. To implement this correctly, select one of the secondary phase conductors and connect it to the ground bus or the grounding electrode conductor. This connection should be made using appropriately sized conductors and connectors, following the guidelines and requirements outlined in the National Electrical Code, specifically NEC Article 250. The size of the grounding conductor must be sufficient to handle the maximum available fault current, and the connection must be mechanically sound and electrically continuous. It's crucial to differentiate between the function of the neutral conductor and the grounding conductor. The neutral conductor, even a 5% neutral, is intended to carry unbalanced load currents under normal operating conditions. In contrast, the grounding conductor is primarily intended to carry fault currents during abnormal conditions such as a short circuit or ground fault. The grounding conductor provides a low impedance path for fault current to return to the source, facilitating the rapid clearing of the fault by overcurrent protection devices. 5% neutral should still be connected to the neutral bus, allowing it to perform its intended function of carrying unbalanced currents. However, it is critically important that the 5% neutral is never bonded to the ground bus or used as the ground reference. Bonding the neutral to ground at the transformer secondary can create a condition known as circulating neutral currents. This occurs when the neutral conductor becomes a parallel path for ground fault currents, leading to excessive current flow in the neutral conductor, voltage drops, and potential overheating. In addition, it can interfere with the proper operation of ground fault circuit interrupters, GFCIs, and other safety devices. Now, let's explore some additional considerations related to grounding 480 delta to 240 delta transformers. Firstly, it is essential to comply with all applicable codes and standards, including the National Electrical Code and any local electrical codes. These codes provide detailed requirements for grounding electrical systems, including transformers, and are designed to ensure the safety of personnel and property. Secondly, ensure that all grounding connections are properly made and tightened. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness and potentially creating a safety hazard. Regularly inspect grounding connections to ensure they are in good condition. Thirdly, consider the impact of grounding on sensitive electronic equipment. In some cases, grounding practices can affect the performance of sensitive equipment, such as computers and communication systems. It may be necessary to implement special grounding techniques, such as isolated grounding, to minimize electrical noise and interference. Now let's explore grounding electrode systems. A grounding electrode system is a network of interconnected grounding electrodes that provide a connection to the earth. The purpose of the grounding electrode system is to stabilize the voltage to ground and to provide a path for fault current to dissipate into the earth. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the minimum requirements for grounding electrode systems, including the number and type of grounding electrodes, the size of the grounding electrode conductor, and the bonding requirements. It is important to ensure that the grounding electrode system is properly installed and maintained to provide effective grounding protection. Now, about grounding impedance. Grounding impedance refers to the total opposition to current flow in the grounding path. A low impedance grounding path is essential for effective grounding protection. High impedance grounding can limit the flow of fault current, which can delay the operation of overcurrent protection devices and increase the risk of electrical shock. Grounding impedance can be affected by factors such as the size and material of the grounding conductors, the quality of the grounding connections, and the type of soil. To minimize grounding impedance, use adequately sized grounding conductors, make sure all grounding connections are clean and tight, and ensure the grounding electrode system is properly installed. You should also consider using a ground impedance meter to measure the grounding impedance and verify that it meets the required levels. Let's discuss ground fault protection. Ground fault protection is a system designed to detect and interrupt ground faults. A ground fault occurs when current flows from a hot conductor to ground, typically through a person or object. Ground fault protection devices, such as ground fault circuit interrupters and ground fault relays, are designed to detect even small ground fault currents and quickly trip the circuit, preventing electrical shock and minimizing damage to equipment. Ground fault protection is required in many locations, including bathrooms, kitchens, and outdoor areas. The NEC specifies the requirements for ground fault protection in different applications. When installing ground fault protection, make sure the devices are properly sized and installed, and that they are tested regularly to ensure they are working correctly. Let's turn our attention to bonding. Bonding is the process of connecting together all metal parts of an electrical system to create an electrically conductive path. Bonding is essential for safety because it helps to equalize the voltage potential between different metal parts, reducing the risk of electrical shock. Bonding also provides a low impedance path for fault current to flow back to the source, facilitating the rapid clearing of the fault by overcurrent protection devices. The NEC specifies the requirements for bonding in different applications, including the size and type of bonding conductors, the methods of making bonding connections, and the bonding of metal water pipes, gas pipes, and other metal parts. To ensure effective bonding, use appropriately sized bonding conductors, make sure all bonding connections are clean and tight, and bond all metal parts that are likely to become energized. Now let's explore surge protection. Surge protection is a system designed to protect electrical equipment from voltage surges. Voltage surges are temporary increases in voltage that can damage or destroy electronic equipment. Voltage surges can be caused by lightning strikes, power line switching, and other electrical disturbances. Surge protection devices, such as surge suppressors and transient voltage surge suppressors, are designed to clamp the voltage and divert the surge current away from the protected equipment. Surge protection is recommended for sensitive electronic equipment, such as computers, televisions, and home entertainment systems. The NEC specifies the requirements for surge protection in different applications. When installing surge protection, make sure the devices are properly sized and installed, and that they are grounded to provide an effective path for the surge current. Let's also discuss harmonic mitigation. Harmonics are distortions in the electrical waveform that can cause problems in electrical systems. Harmonics can be caused by nonlinear loads such as electronic equipment, variable frequency drives, and fluorescent lighting. Harmonics can lead to increased current flow, overheating of equipment, and interference with communication systems. Harmonic mitigation techniques include using harmonic filters, reactors, and transformers designed to reduce harmonics. The NEC specifies the requirements for harmonic mitigation in different applications. To reduce harmonics, identify the sources of harmonics in the electrical system, implement harmonic mitigation techniques to reduce the harmonics, and monitor the harmonic levels to ensure they are within acceptable limits. Regarding voltage drop is the decrease in voltage that occurs along a conductor due to the resistance of the conductor. Excessive voltage drop can cause problems with electrical equipment, such as reduced light output from lamps, reduced motor torque, and malfunction of electronic equipment. Voltage drop can be calculated using Ohm's law. The NEC specifies the maximum allowable voltage drop for different types of circuits. To minimize voltage drop, use adequately sized conductors, reduce the length of the conductors, and reduce the load current. To summarize, grounding the 480 delta to 240 delta transformer correctly is a matter of applying engineering and electrical knowledge and following the established NEC guidelines to enhance personnel safety, protect equipment, and maintain the integrity of the electrical system.